Welcome to Lecture 3.5, Complex Inner Products and Fourier Series. Let's begin with a quick review of complex numbers. I'm assuming that you've seen this before, but even if you haven't, it should be elementary enough that you can pick it up pretty easily. So the most important result is called Euler's formula, which says that e to the I theta is equal to cosine of theta plus I sine of theta. If you haven't seen this before, this seems like a minor miracle, and I'll draw some pictures shortly, but first let me show you a few consequences from this. So remember that cosine of negative theta equals cosine of theta, and sine of negative theta equals negative sine of theta. So I like to say that cosine absorbs negative signs, and in sine they get pulled out. So using these two identities with Euler's formula gives us the following. E to the negative I theta equals cosine of theta minus I sine of theta. Now if we add these things together, the signs cancel, and we get e to the I theta plus e to the minus I theta equals 2 cosine of theta. So this gives us a formula for cosine of theta, namely cosine of theta is e to the I theta plus e to the minus I theta over 2. Now similarly, if we subtract these two things, so let's do that. Let's now subtract these. Then the cosines cancel, and we get e to the I theta minus e to the minus I theta equals 2I sine of theta. So we have a formula for sine of theta. Namely, sine of theta equals e to the I theta minus e to the minus I theta divided by 2I. Now I told you to just trust this formula, Euler's formula. Let me draw a few pictures to try to convince you as to why this is true. So here's the unit circle. I think I might have done this before earlier in the class, but again, it never hurts to see it twice. So if you take any point on the unit circle, this is radius 1, and this is angle theta, then this is e to the I theta. And that's true with anywhere on the unit circle. So that means that e to the 0 equals 1. And if you take e to the pi, so this point is e to the pi, or e to the I pi, that's equal to negative 1. And we know by trig, basic trig, that this is cosine of theta, and this height is sine of theta. And if this is the real axis and this is the imaginary axis, then e to the I theta is cosine of theta, the real part, plus I sine of theta. So that's all Euler's formula is. It's cosine of theta plus I sine of theta. Okay, and I guess the only thing I haven't explained is why this point on the unit circle is e to the I theta. That's just polar coordinates, and I guess I don't know what else I could say to convince you of that. But if you believe that, then Euler's formula is just basic trigonometry. Okay, so e to the minus I theta, that corresponds to the point, if you take the minus theta, that's down here. So this is e to the minus I theta. So this is naturally cosine of theta minus I sine of theta. Now, also really important is to remember that if you have in polar coordinates, or in the complex numbers, let's take something z, let's write it as a plus bi. Again, we can write this is angle theta, we can write this as e to the I theta, and then I got to multiply by whatever this distance r is. Let's call that capital R. Let me put the capital R here. And now what is r? R is, well, by the Pythagorean theorem, this is a and this is b. So by Pythagorean theorem, r is the square root of a squared plus b squared. So that's what z is. Remember that z bar, let me put that down here. So z bar, this is the complex conjugate. This is a minus bi. And this is equal to r times e to the minus I theta. So I want you to see why this is true both in Cartesian coordinates, a plus bi versus a minus bi, and why it's true in polar coordinates, r e to the I theta, r e to the minus I theta. Of course, this angle here is negative theta. And finally, remember how you multiply any two complex numbers. Their lengths multiply and their angles add. Now, it's not clear how you see that if I say, what's a plus bi times c plus di, it's not at all clear why that's the case. But if I were to write this as, let's get a pen, r1 e to the I theta 1 times r2 e to the I theta 2, if I were to write these things in polar coordinates, now it's easy to see that this, again, these are the lengths, r1 and r2. You multiply these as numbers, you get r1, r2. The lengths multiply, and the angles add. So the angles adding is e to the I theta 1 plus theta 2. That's the laws of exponents. So one special case of this is if you multiply e or z times z bar, so you get z times z bar, that's r e to the I theta times r e to the negative I theta. You can already see the angles are the opposite, so they add to be 0. So we get r squared e to the 0, which is r squared. So if we were to draw that on here, let me write this. So this is z times z bar, and this is the square of r. So this is equal to r squared. So here it makes sense to say that the norm of z, this is equal to r. It's just the length, the distance from z to the origin, just like how the absolute value of a number on the number line is the distance from that number to the origin. The same thing, this is r. This is the square root of a squared plus b squared. So remember that piece. This is going to be important. We will use this fairly shortly. At this point, I want to say a few important differences between real and complex vector spaces. So until now, we've been primarily dealing with R vector spaces, or real vector spaces, and things are a little different with complex vector spaces. Now, if we're just adding up vectors or multiplying by scalar multiples, it doesn't really matter if we allow real numbers or complex numbers. The difference comes in to play when we are dealing with inner products. To understand why things are different with C vector spaces, let's compare the notion of norm for real versus complex numbers. Now, I've given you a slight preview in the previous slide. For any real number, x, its norm, the distance from 0, is just the absolute value of x, which is the square root of x squared, and that's a real number. Well, it's actually a non-negative real number. For any complex number, z equals a plus bi, its norm, also its distance from 0, is defined as follows. So we write it with an absolute value sign again, and it's defined as the square root of z times z bar. In other words, the square root of a plus bi times a minus bi, which is the square root of a squared plus b squared. So that's what I showed you in the previous slide. I drew a picture for that. But now let's go from the real numbers and the complex numbers, r and c, to r squared and c squared. For any vector v in R2, let's say v1 and v2 are the entries, its norm, or the distance from 0, is defined as follows. So we write norm v, sometimes with a double absolute value sign. Some books just write it with one bar, like this. That's just the square root of v dot v. Note that v dot v is just v transpose v, and to see that, v dot v, one way to write it is v1 and v2 on the side times v1 and v2 here, and so that's v1 squared plus v2 squared. So the square root of v transpose v is the square root of v1 squared plus v2 squared. So compare what we have here to what we have up here for complex numbers. So the only difference here is we don't have a bar over here, but we don't need that because everything here is a real number. Similarly, for any vector z in C2, so this is a vector of two entries, z1 and z2, say z1 is a plus bi and z2 is c plus di, its norm is defined as follows. So we write norm z as before. This is the square root of z bar transpose times z. So again, compare this to what we have up here, v transpose v. We could put a bar on top of v, but we don't need to because everything is real. Similarly, for any complex vector z in C2, so this consists of two components, z1 and z2. Let's say z1 is a plus bi and z2 is c plus di. Its norm is defined as follows. So we write norm z like we do norm v, but now we define this as the square root of z bar transpose times z. Compare that to what we have up here, v transpose v. The only difference is we don't have a bar up here, but we could put a bar up here because everything's real. So the complex conjugate of a number or a vector, if it's real valued, is itself. So these really are the same thing. And this, of course, instead of being v1 squared plus v2 squared, it's z1 norm squared plus z2 norm squared. So think of it like this now. So now we have a minus bi, c minus di. We're taking the product of that with a plus bi and c plus di. So take the normal dot product, this product times that product, and what do we get? Well, this is a squared plus b squared, so this is a squared plus b squared plus c squared plus d squared, and that's equal to the norm of z1 plus the norm of z2. Let's compute two quick examples of this. Let's compute the norms of the vector 1, 1 and the vector I. So we'll start with 1, 1. If v equals 1, 1, then the norm of v is, it's the square root of v transpose times v. So that's just the square root of 1 plus 1, which is root 2. And now if v is I, then the norm of v is, we take the complex, we take the transpose and the complex conjugate, multiply that by v, so it's I bar times I. It's the square root of this. And now complex numbers, if I is up here and then this down here, this is I bar, but it's also equal to negative I. So I times I bar, one way to see it is the angles add, you get 0, the lengths multiply, you get 1. Or you can just see it as negative I squared, and that's negative 1. So this is the square root of 1 plus 1, which is equal to 2. Now, why do we need this? So why do we need this complex conjugate here? Let's see what happens if we didn't do it. So let's notice that if we were to try to just take z bar, or if we were to try to just take z transpose times z, we would get I squared plus I squared, which is negative 2. And we obviously can't take the square root of that, but we could. We'd get a negative number, or an imaginary number. And the norm, key thing here is this norm, it has to be a real number. Not only does it has to be real, but it has to be a non-negative real number. Just like up here, the norm of a real number, it has to be a non-negative real number. We can't get a negative number, we can't get an imaginary number. Here's the big idea. The norm in a real vector space is defined using a real inner product. And for example of that, one example is the dot product. That is a real inner product. V dot W you can define as V transpose W. Some people define it as VW transpose. It doesn't really matter. That's this vector W transpose times V. This is what it looks like in matrix notation. And of course, that's the sum of vi times wi. You just multiply these entries together and add them up. Now compare that to the norm in a C vector space. That's actually defined using what we're going to call a complex inner product. And an example of that we saw is z dot w. Now when I say dot, it's assumed that we are in a C vector space because we define things differently. We're going to define this as w conjugate transpose z. And that is w conjugate transpose. So take w, put it on its side, put conjugates in every entry, and multiply that by z. And that is the sum of the products of these. So this is like an ordinary dot product, z1 times w1 bar plus z2 times w2 bar, so forth. We add those up. Now, some books or some people will define this the other way. They'll say this is defined as z transpose bar w. That's fine too. It doesn't really matter. I mean, they give you slightly different things, but for all intents and purposes, one of them is just as good as the other, as long as you're consistent. Okay, so let's define what a complex inner product is. We've defined what a real inner product was in the first series of lectures. So let's let V be a complex vector space. A function that takes in two vectors, so two inputs, and spits out a real number is a complex inner product if it satisfies the following for all vectors u, v, and w and all constants c. So first of all, it has to be what's called bilinear. So sums split apart. So u plus v dot w is u dot w plus v dot w. Second property is that if we have a constant inside the first argument, we can just pull it out. So cv dot w is c times v dot w. But if we have a constant in the second argument, we pull it out, we have to put a bar out in front. So v dot cw is c bar times v dot w. Let's see why this is. Let's go up here, and I'm going to write z dot w with angle brackets, so z dot w, so inner product notation. Now on top, let's look at what we get if we do cz dot w. Well, if I do that, then I'm going to write this as w1 bar up to wn bar times c z1 up to c zn, and now I can just pull this constant out, and I can write this as c times z dot w. However, if I have z dot cw, now this is equal to cw1 bar, and if a bar over both of these is the same as a bar over each one, basic properties of complex numbers, and then c bar times wn bar times z1 dot 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 zn. And now if I want to pull out the c, you can see it's a c bar, so I can write this as c bar z dot w. And I should say that, I think I said before, that some books reverse the roles of z and w. So z dot w is z bar transpose times w. It doesn't matter as long as you're consistent. If you switch the roles of this, then you got to switch the roles of where the bar is. So in this case, if you pull the c out from the first argument, you put a bar here, and if you pull it from the second argument, you don't put a bar here. If I remember right, I think I'm using what's more common for mathematicians, and I think physicists usually do it the other way around. So I think physicists are going to put a bar here and not a bar there. Though it doesn't matter as long as you're consistent. Okay, the third property is that v dot w is the complex conjugate of w dot v. So this is in red because it's different from the real case. Remember that for a real inner product, dot products are symmetric. So v dot w is w transpose v, which is w1 up to wn, and v1 up to vn. And of course it doesn't matter. We can write this if we wanted to as v transpose times w1 up to wn. So this is v transpose w, which is w dot v. So things are completely symmetric in the real case. It doesn't matter what order you take the dot product. In the complex case, it's a little bit different. So if this is, let's do it up here, if this is z dot w, or z dot w is this, let's look at what w dot z is. So w dot z is z transpose bar w, which is, that's z1 bar dot 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 zn bar times w1 up to wn, and that is, and these things are not, this product is not equal to that product. Now it is if we take the bar of this whole thing, because we can always just split up that. So taking the complex conjugate, that thing is just equal to z1 dot 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 zn. Oops, I didn't mean to do that last one. z1 up to zn, w1 bar up to wn bar, and you can clearly see that this product is equal to that product. Both of them are equal to this sum right there. Okay, so this is sometimes called skew symmetry. It's not symmetric, or conjugate symmetry. That's maybe a better word for it. And finally, the last property is just the same as in the real case. V dot v has to be real and non-negative, and equality only holds for the zero vector. At this point, I want to turn our attention to vector spaces of functions, in particular complex vector spaces of functions. So let's recall the R vector space, and here I'm slightly abusing terminology because I'm going to allow infinite sums, to be the span of the cosine terms and the sine terms. We can do the same thing, but instead of allowing coefficients from R, let's allow coefficients from C. Doesn't really change things much. Well, now instead of this basis is perfectly fine, cosines and sines, but we have another way we can write things. Recall from the very first slide that we can write cosine of nx as e to the inx plus e to the minus inx over 2, and sine of nx as e to the inx minus e to the minus inx over 2i. So because of this, instead of using these sines and cosines, there's a better way to write these functions using a different basis, namely this basis. Consider the span of all of the complex exponentials. And as before, I'm going to cheat a little bit and allow infinite sums because we can get away with that. Here's a remarkable thing. It turns out that this basis is orthonormal with respect to the following complex inner product. So f dot g is defined as 1 over 2 pi times the integral from negative pi to pi of f of x times g of x bar dx. Now, it's quite easy to verify this. So what does it mean when I say this basis is orthonormal? That means if I take the dot product of e to the inx and e to the imx, then I better get 0 if n and m are different and 1 if they're the same. This inner product, by definition, is 1 over 2 pi times the integral from negative pi to pi of e to the inx times e to the imx bar dx. Now let's think about what that is. Let's go back to our unit circle, and don't forget that if you have any point on the unit circle with angle theta, this is e to the I theta. And then down here, this is e to the I theta bar, which is e to the negative I theta. So in other words, whenever you take the complex conjugate of e to the I something, we just make that exponent a negative. So in other words, this integral is 1 over 2 pi times negative pi to pi times e to the inx e to the negative imx dx. And I'm going to write this as 1 over 2 pi times integral from negative pi to pi of e to the I n minus m x dx. Okay, now I'm going to box this, and let's think about what this is. So there's two cases. If n and m are equal, then this just whole thing reduces down to e to the 0, which is 1. Let me do that case right here. I'm going to say, suppose n equals m. So if n equals m, now we have 1 over 2 pi times negative pi to pi of the function 1 times dx. So that's 1 over 2 pi times x from negative pi to pi. So that's 1 over 2 pi times pi minus negative pi. That's 2 pi, so that's equal to 1. So if n and m are equal, then this inner product is 1. In other words, each of these functions has norm 1. Let's verify that they're orthogonal. So now let's assume that if n is not equal to m, let's verify that the integral is indeed 0. So now we get this is equal to 1 over 2 pi times, well, let's take this integral. So the integral of e to the k times x is just e to the kx divided by the constant k. So I can write this as, so I can divide by I times n minus m. And I'm going to write this as e to the I times n minus m x from negative pi to pi. So what is this? This is 1 over 2 pi I times n minus m, and n minus m is non-zero, so we can divide by that. But now we have, let's see, we have e to the I times n minus m pi minus e to the I times n minus m negative pi. So I'll put a pi there and a negative pi, or negative sign right there. Now, I claim that this is equal to 0. Let's think about why that is. Okay, e to the I times n minus m, this is an integer. So what is e to the I k pi? What is that if k is an integer? Remember, if k is an even integer, then we are at like 0 pi, or if k is an even integer, then we're right here. This is 0 radians, 2 pi radians, 3 pi radians, or 4 pi radians, 6 pi radians. This is pi radians, 3 pi radians, 5 pi radians. So e to the I k pi is negative 1 to the k, always. So this is equal to, this here is equal to negative 1 to the n minus m, and this is equal to negative 1 to the negative m minus n. And those are the same. Now we'll be careful. We switch. This is positive, or one of these is positive, one of these is negative. That doesn't matter. Start from here. If you go take 3 pi radians, you're going 1, 2, 3 times around. But if you go negative 3 pi radians, you end up in the same place. 1, 2, 3 times around. If you go 6 or 4 pi radians, 1, 2, 3, 4, or negative 4 pi radians, 1, 2, 3, 4, you end up in the same place. So it's easy to see that e to the I k pi is e to the negative I k pi negative 1 to the negative k. Another way to see that is this is just 1 over negative 1 to the k. And if you're dividing by plus or minus 1, it doesn't change your result. So this is indeed equal to 0. And so yes, we verified that these two functions, or the inner product of these two functions, is either 1 if they're the same and 0 if they're not. And that's what it means for this basis to be orthonormal. This was a lot easier to check. Remember how we had to check the sines and cosines being orthonormal? Now, I didn't actually do it, but I said you would have to verify that. Remember that the integral of cosine of nx times cosine of mx dx from negative pi to pi of 1 over pi, that had to be either 0 or 1. 0 if n and m were different, and 1 if n equals m. Then we had to do the same thing for two different sine waves. And then we had to show that the inner product of integral of a cosine and a sine was always 0. And then we really had to do it for 1 with a cosine and 1 with a sine. And this integral is not fun to do. I said it was easy. Cosine of nx, cosine of mx. What sort of trig identity would you use for that? Think about that. What would you use? Well, the short answer is that you use Euler's formula, or use that, or the related one to Euler's formula, cosine of nx. This integral is actually fairly straightforward if you write it as complex exponentials. E to the I nx plus e to the minus I nx divided by 2. If you do these identities, then you can figure this out without too much trouble. But that still is much harder than this simple integral here. So not only are the integrals more complicated, but you got to do a lot more of them because you have a mixture of sines and cosines. And you had that 0 term, the 1, which, remember how things were a little bit weird with that square root of 2, and that a naught over 2? That's because we had this asymmetry of this doubling up here. This is a much cleaner basis. This is just complex exponentials for all exponents, or all integers, positive, negative, 0, etc. So this is arguably a much more elegant way to write Fourier series than sines and cosines. Now, the advantage of the real Fourier series up here is that we can visualize these as functions. We know what sine waves and cosine waves look like. We can't really graph these things in quite the same manner. Okay, let's clean this up and summarize a bit. So we have the space of 2 pi periodic functions with complex coefficients. Instead of using sines and cosines, we can use complex exponentials. And if we tweak the inner product, so we have to put a 2 here, and we have to put a complex conjugate here. We didn't even need to deal with that before because everything was real, but now we need to worry that we have a complex conjugate here. So with this inner product, these complex exponentials are orthonormal, because if we take the inner product of any two of them, e to the I nx and e to the I mx, defined as this integral, what do we get? We get either 0 or 1, depending on whether n and m are equal. So we get 1 if m and n are equal, and 0 if they are different. Okay, now we come to the formal definition of complex Fourier series. So before I begin, I should say that what we did in the previous slide, everything was 2 pi periodic, and our orthonormal basis was a set of all e to the I nx, where n was an integer, positive or negative or 0. So this is when we're looking at the space of 2 pi periodic functions. In general, if we're looking at the space of 2L periodic functions, now our basis has to be e to the I pi nx over L when n is in any integer. So it's just like what we did before. Remember, we had things like cosine of nx, and for the general case, we had cosine of n pi x over L. And things are very nicely when L is equal to pi, that everything's cancel, or when L is 1, it's not as bad either. Okay, so given this, if f of x is a piecewise continuous 2L periodic function, then its complex Fourier series is a way to write the function as an infinite sum of these orthonormal basis vectors. So Cn times e to the I pi nx over L. Now notice this is a doubly infinite sum, which is a little bit weird psychologically, that we're adding things up in both directions infinitely. But there's another way to write this. If you want to, you can pick out the n equals 0 term and then just add the infinite sum from 1 to infinity. Now we just have an infinite sum in one direction. where we pair the n terms and the negative n terms together. So Cn e to the I pi nx over L plus C negative n I to the I pi negative n x over L. So these both have their pros and cons. Sometimes it's nice to write it this way because the formula for C naught ends up being a little bit different than the one for the Cn's because the integral is different. So it's if you have a formula for the Cn's that works for all but one case, you can't really plug it into here. You sort of have to pull out that weird case and then plug them back into here. Okay, so these Cn's, these, as before, you can think of this as how much of f is in this direction, is in the magnitude of this unit basis vector. So that's just a projection of f onto this particular function. So C naught, I don't remember if I said that the Cn's are called the complex Fourier coefficients, but that's what they are called. C naught is the projection of f onto 1, or the inner product of f and 1, which is 1 over 2L times the integral from negative L to L of f of x dx. Now I should say we have a different basis, so we have to have a different inner product, just like what we did for the real case. Everything is slightly different. We're just replacing pi's with L's. Okay, so this is what C naught is. Oh, and I should say that in this case, it's easy to check that the norm of the function 1 is 1 over 2L from negative L to L, 1 dx, which is 1 over 2L times x from negative L to L, which is equal to 1. So remember in the real case when the norm of the function 1 was like root 2, and that was annoying? Yeah, so that doesn't happen here. So that's arguably why this is a more elegant way to deal with Fourier series. Okay, so that's what C naught is. Cn is just the projection of f onto e to the I pi nx over L. And that's also defined by an integral. 1 over 2L times the integral from negative L to L of f of x e to the negative I pi nx over L dx. Let's do an example. Let's find the complex Fourier series of the following function, which I claim is a square wave. Let's sketch this first. So here's that function. This is pi. This is 2 pi. And this is negative pi and negative 2 pi. So this function is defined to be 1 from 0 to pi and negative 1 from pi to 2 pi, and then it's repeated like this. And so over here it's negative 1, and here it's positive 1, and so forth. So I could have actually defined this, instead of saying from pi to 2 pi, I could have defined it from negative pi to 0, if I wanted to, and that gives me the same function. And as before, I'm not defining what this function actually is at these points of discontinuity, because I won't actually have control over what that is once we have the Fourier series. It will, not surprisingly, converge to this average value. Okay, so where do we want to start? So C naught. C naught is, well, this is the constant term, so it should be the average value of this function, and that's equal to 0. So if you don't believe me, you can check 1 over 2 pi times the integral from negative pi to pi of f of x dx. So this is the area under the curve of this function from negative pi to pi. That's clearly 0, because this area cancels with that area. Okay, so Cn now. Cn is 1 over 2 pi times the integral from negative pi to pi of f of x e to the I n x dx. Well, it's the complex conjugate of this, so we got to put a negative sign in front of that. Okay, so let's compute this. Well, now, even though this is an odd function, we can't use any odd symmetry because we are dealing with complex exponentials, so we really just have to break this into two integrals, this part and that part. So if we do that, this is 1 over 2 pi times negative pi to 0 of negative 1 times e to the minus I n x dx, negative 1 here, and it's positive 1 on that part. So this is plus 1 over 2 pi times 0 to pi times positive 1 times e to the negative I n x dx. Okay, so let's compute these two integrals. I've got to be really careful with signs. It's so easy to make a mistake. So this is negative 1 over 2 pi. Now, the integral of this is e to the I n x, and we have to divide by negative I n x. So I'm going to put that I n right there and put the positive sign there. And we're going from negative pi to 0. I should have left myself a little bit more room. Oh well. And now plus 1 over 2 pi, and now we have to divide through by this constant I n x, so, or I n, and then a negative sign goes there. And so we have e to the negative I n x from 0 to pi. Now remember, I'm going to write it up front. Up top, e to the I n pi equals e to the negative I n pi, which is negative 1 to the n. Does not matter if this is plus or minus. So this thing here is equal. This first one is equal to e to the, so that is equal to 1 over 2 pi I n. And we plug in 0, we get 1. And we plug in pi, or negative pi, into here, we get negative 1 to the n. So we get negative 1 to the n. And now minus 1 over 2 pi I n. If you plug in pi into here, you get negative 1 to the n. If you plug in 0 into there, you get 1. So we get this sum, and if we add this up, so notice this negative sign is here, and this thing, so we flip the order of that, that becomes positive. So really what we get is we get 1 over this 2 is we get double of this because of the negative and the negative there. So we get 1 over pi I n times 1 minus negative 1 to the n. And if you want to, some people don't like having i's in the bottom of this, so if you want to, you can write this as negative I over pi n times 1 minus negative 1 to the n. So in other words, f of x is the infinite sum from n equals negative infinity to positive infinity of negative I over pi n times 1 minus negative 1 to the n times e to the I n x. And well, since c naught is equal to 0, I really should say, well, actually, I can leave it like this, because if n is equal to 0, we get 1 minus 1 and we get 0. Well, we're dividing by 0 here. So yeah, let me just say n is not equal to 0. So this is the complex Fourier series of this square wave. It is a way to write this square wave as an infinite sum of complex exponentials. We'll conclude with one more example. So let's compute the complex Fourier series of the 2 pi periodic extension of the function e to the x defined from negative pi to pi. So here's what I mean by that. So here is a function, and from negative pi to positive pi, let's say this function is e to the x. Well, let's just repeat that to be, copy-paste that to be periodic and compute the Fourier series of this. So this is what f of x is equal to. So notice this would be a pain to do in a real Fourier series, because we would have to integrate e to the x times cosine and e to the x times sine. It's neither even nor odd. And that would just be annoying to do, because that's not a fun integral. So the complex Fourier series is going to end up being a lot easier. And compare that to the last problem, the square wave. The complex Fourier series was arguably harder because it was because we didn't have that even and odd symmetry that we could use right away. Okay, so let's do this. So C naught is the average value. This is not going to be 0 anymore because the average value is non-zero. So C naught is 1 over 2 pi times negative pi to pi. the function e to the x dx. So this is 1 over 2 pi times e to the x times negative pi to pi. So that's, let's see, what is that? That's e to the pi minus e to the minus pi over 2 pi. That's c naught. Okay, that's a little weird. So what's Cn? So Cn is 1 over 2 pi times the integral from negative pi to pi times e to the x, e to the negative I n x dx. Oops, dx. So that is, see, that is 1 over 2 pi times the integral from negative pi to pi. We can combine these exponentials into 1, e to the 1 minus I n x dx. And if we do this, this is 1 over 2 pi times 1 minus I n times e to the 1 minus I n x from negative pi to pi. Now, what do we do here? Okay, so let's see. I'm going to write this as follows. I'm going to write this as 1 over 2 pi 1 minus I n times e to the pi times e to the negative I n pi. So I can break these up using rules of exponents. And then minus, so this is, again, this is e to the x and e to the times e to the negative I n x. So this is e to the negative pi times e to the negative I n x, and we're plugging in negative pi, so we get positive I n pi. Remember that e to the I n pi is e to the negative I n pi, which is negative 1 to the n. So this, both of these things are just negative 1 to the n. That's negative 1 to the n, so we can factor that out. And we can write this as negative 1 to the n over 2 pi 1 minus I n times e to the pi minus e to the minus pi. So this is equal to C naught. So we can write our complex Fourier series as f of, so this is where it actually, it helps to write it as C naught. Oh, let me undo that as C naught, which, let me write this down here. So this is e to the pi minus e to the minus pi over 2 pi plus the infinite sum from n equals 1 to infinity of this creature. So this is, well, let me just remind you, this is C naught. And so this first one is negative 1 to the n over 2 pi 1 minus I n times e to the pi minus e to the minus pi times e to the I n, oops, I don't want to write pi, I n x. So this, that's my Cn. And then the next one is c to the minus n. So I just take this thing and I plug in minus n for it. So I get negative 1 to the negative n, which is, remember that negative 1 to the n equals negative 1 to the negative n. So I'm going to leave that as negative 1 to the n over 2 pi times 1 plus I n. Because if I plug in a negative n in for here, I get a positive sign. And then everything else is the same. This is e to the pi minus e to the minus pi times e to the negative I n x. So this is c to the negative n. So on an exam, if I were to just tell you compute the complex Fourier series, you wouldn't have to do everything I just did here. You would just have to give me a formula for C naught and one for Cn. The formula for C negative n is the same thing. You're just plugging a negative n for an n. So this is the best way to write this. This is why that version where you plug out the C naught is useful, because if you had this doubly infinite sum of n equals negative infinity to infinity, Cn e to the I nx, you wouldn't really have one formula for this because you got two cases, the Cn and the C naught. And finally, some of you may not like the fact that I'm putting an I in the bottom of the fraction here. You know, it's always nice if you have like 1 over 3 minus 2i to not leave it like this. You want to write this in a plus bi form. Remember that? Remember what you do about this? So if you multiply by 3 plus 2i times and 3 plus 2i on top and bottom, you rationalize this, and now you get 3 plus 2i, and then you have difference of squares. This is 9 minus negative 4. So this is 9 plus 4. This is 9 plus 4 is 13. So if you want to rationalize this denominator, you can. You don't need to. Now, in our next lecture, when we want to go between the real and the complex Fourier series, that will be really useful to do. But we're not there yet. We don't need it. So for right now, we're just going to say this is the complex Fourier series. With this answer, we're done. But more on this in the next lecture, so stay with us.